A frozen world at the solar system's edge defies our understanding of distant planets. This is Orcus, a dark and icy dwarf planet lurking in the Kuiper Belt, a cosmic twin to Pluto in size and orbit. Yet this remote world is wrapped in layers of profound and unexplained mystery. By the end of this journey, you will know the 25 most baffling enigmas that scientists are scrambling to solve. Why does it lack the atmosphere its twin possesses, and what is the strange nature of its alien moon? What cosmic secrets do you think a world this ancient could possibly hold? The first and perhaps most fundamental mystery of Orcus is what happened to its air. We expect worlds of a certain size and distance to hold onto a blanket of gases, yet Orcus appears to breathe nothing into the void around it. This stands in stark contrast to its celestial twin, Pluto, which is famously swaddled in a thin but detectable haze of nitrogen and methane. Both worlds are similar in size, and both endure the same profound cold in the outer solar system. The basic physics of planetary science suggest that Orcus, too, should have managed to cling to some form of atmosphere. So where did it go? One compelling theory suggests we might simply be looking at the wrong time. Pluto's own atmosphere is known to pulse and fade, collapsing to the ground when it is at its most distant and coldest point in its long orbit. Orcus follows an even more elongated path around the Sun, a journey that takes 245 years to complete. It is entirely possible that our telescopes have only studied this distant world during its deep freeze, a period when its entire atmosphere has snowed out onto its icy surface, leaving it naked and exposed to the vacuum of space. We may just be witnessing a world in hibernation. Another possibility is that the atmosphere is not gone, but has simply transformed into something we are not equipped to easily see. Perhaps it is not composed of the expected nitrogen, but of heavier, more sluggish gases like carbon monoxide. Such an atmosphere would be incredibly thin and tenuous, clinging so closely to the surface that our current instruments simply cannot distinguish it from the ground ice below. Or the answer could be far more dramatic. A cataclysmic impact in the ancient past might have stripped the world of its volatile gases in a single, violent event, leaving it an airless husk. Solving this atmospheric riddle is crucial because it forces us to question our entire understanding of how small, cold worlds work. What makes one twin thrive with a dynamic, changing sky, while the other appears as a silent, frozen statue? The answer will redefine the line between a living world and a dead one in the darkest reaches of our solar system. If the missing atmosphere is the first mystery, then the alien nature of its moon is the second. Orbiting Orcus is Vanth, a companion nearly as large as the dwarf planet itself, yet it could not appear more different. While Orcus reflects sunlight with a bright, icy sheen, Vanth is a dark, dusky charcoal gray. This stark contrast in color and brightness is the central clue to a profound puzzle. Two objects so close together, locked in a gravitational embrace, should be made from the same primordial stuff. Their surfaces should tell a similar story of the solar system's early days, but they do not. This fundamental difference screams that Vanth has a history entirely separate from the world it now circles. The most compelling explanation is that Vanth is a captured object, a wanderer from the distant Kuiper Belt that was snared by Orcus's gravity in the ancient past. This would account for its foreign appearance, as if two strangers from different cosmic neighborhoods were forced to share a home. But this theory only deepens the mystery. What kind of object is Vanth exactly? Its dark surface suggests it is rich in carbonaceous material, the same dark, primitive stuff found in some asteroids. This has led to a fascinating idea that Vanth might be what scientists call a rubble pile, a loose collection of rock and ice held together by its own meager gravity. It could be the shattered remnant of a much larger body destroyed in a cataclysm long ago. Alternatively, it might be a leftover building block from the solar system's formation, a pristine time capsule that never grew into a planet. The giant impact hypothesis presents another tantalizing possibility. Perhaps a colossal collision shattered an early version of Orcus, and Vanth is a large fragment of that event that managed to coalesce and remain in orbit. Yet if that were the case, why is its composition so different from the bright, icy surface of its parent? The answers lie locked within that dark surface, and until a spacecraft visits this remote system, the true nature of Orcus's shadowy companion will remain one of its most enduring secrets. These bright patches are the third great puzzle of this distant world. Scattered across the surface of Orcus are areas of stunning, almost pure whiteness, reflecting sunlight with an intensity that defies the darkness around them. They gleam like fresh snow under a street lamp, standing in stark contrast to the duller, reddish terrain that makes up most of the dwarf planet. On an object billions of years old, such pristine whiteness should be impossible. The constant bombardment of cosmic radiation over eons should have baked and darkened these ices, transforming them into a gunk-like substance scientists call tholins. This is the same process that gives many other Kuiper Belt objects their characteristic rusty, brick-red color. So why do these brilliant spots on Orcus look so clean, so new? One of the most thrilling explanations is cryovolcanism. Imagine not volcanoes of molten rock, but of freezing slush. Deep beneath the frozen crust of Orcus, reservoirs of water mixed with ammonia or other antifreeze agents might remain liquid. When the internal pressure builds, this slushy mix could erupt onto the surface, spreading a fresh, radiant layer of pure ice that instantly covers the old, darkened landscape. This would mean Orcus is not a dead, static ball of ice, but a world with a beating geological heart capable of renewing its own face. Alternatively, the answer might lie in the strange behavior of ices in the vacuum of space. Some theories suggest that over millions of years, the very faint heat from the distant sun could cause a process called thermal migration. More volatile ices, like methane, might slowly sublimate from warmer areas and then refreeze onto the coldest patches, effectively concentrating and purifying the brightest ices in specific permanent cold traps. This would create natural bright spots without the need for violent eruptions, a slow and steady self-cleaning process. The existence of these brilliant stains forces us to reconsider the nature of cold, distant worlds. Are they simply inert fossils, or can they harbor hidden, sluggish geological activity that occasionally bursts into view? The next time you look at a patch of freshly fallen snow, consider that the same impossible cleanliness might be happening on a tiny, frozen world at the very edge of our solar system. This gravitational lockstep with a giant planet is the fourth and most intricate mystery of Orcus. The dwarf planet is caught in a precise cosmic rhythm with Neptune, a phenomenon scientists call an orbital resonance. Think of it as a carefully timed dance across the solar system. For every 3 laps that the ice giant Neptune completes around the Sun, the distant Orcus completes exactly 2. This is not a chance alignment. It is a stable, repeating pattern that has likely persisted for billions of years. How did this fragile partnership between a tiny world and a gas giant begin, and how has it survived the chaotic gravitational turmoil of our solar system's youth? The prevailing theory points to a grand migration in the ancient past. Astronomers believe the giant planets, including Neptune, did not form in their current positions. They shifted and drifted outward, their immense gravity scattering smaller objects like icy pebbles in their wake. During this great migration, Neptune's gravitational influence could have captured Orcus, nudging it into this specific resonant orbit, a stable niche where their gravitational pulls harmonize rather than conflict. This resonance acts as a shield. The synchronized orbits prevent Orcus and Neptune from ever getting too close, ensuring their gravitational interactions are gentle and repetitive, not disruptive. It is a cosmic agreement that protects Orcus from being flung into a different orbit or even ejected from the solar system entirely. But this solution creates a new question. Is Orcus a unique case, or is it merely one of the most visible members of a hidden population? This specific 2 to 3 resonance defines an entire class of objects known as Plutinos, small bodies that share Pluto's peculiar orbital relationship with Neptune. Orcus, as one of the largest known Plutinos, suggests this gravitational niche is crowded with countless other, smaller worlds we have yet to discover. Their collective existence is a ghostly echo of the solar system's violent reorganization, a frozen record of planetary migration written in the paths of icy dwarfs. The resonance riddle forces us to see Orcus not as an isolated world, but as a single note in a vast gravitational symphony, its path through the darkness dictated by a dance that began before life on Earth even existed. This wildly stretched orbit is the fifth and most dynamic mystery of this distant world. Orcus does not travel in a neat, circular path like the planets closer to the Sun. Instead, its journey is a long, drawn-out ellipse, a cosmic roller coaster that carries it from the relative inner edge of the Kuiper Belt to a point nearly twice as far out into the cold. This extreme ellipticity creates an environment of radical change. The amount of solar energy reaching Orcus at its closest approach is 4 times greater than what it receives at its most distant point. For a world that might harbor volatile ices on its surface, this is a recipe for chaos. Imagine a climate where the difference between summer and winter is not a matter of a few degrees, but a cataclysmic shift between a deep freeze and a relative thaw. This wild swing makes the idea of a stable climate, or even predictable seasonal cycles, nearly impossible. Any tenuous atmosphere that might form would likely be boiled away during the close pass, only to snow back down into a deep freeze for the majority of its long year. This bizarre orbit is not a random fluke. It is almost certainly a fossil record, a permanent scar from a violent gravitational encounter in the solar system's youth. The most likely culprit is Neptune. As the ice giant migrated outward billions of years ago, its immense gravity would have acted like a slingshot on small, primordial worlds like Orcus. A close pass could have yanked the dwarf planet from a more circular path and hurled it into this stretched and eccentric orbit we see today. Its current resonant dance with Neptune is the stabilized aftermath of that ancient chaos, a truce called after a gravitational battle. This dynamic history makes you wonder what strange seasonal phenomena might occur there. Could there be a brief, explosive period of geological activity when Orcus swings close to the Sun, with volcanoes erupting slushy water before the world freezes solid again for 2 centuries? Might its surface be a patchwork of terrain, each layer representing a different extreme in its tumultuous climate history? The elliptical path of Orcus is more than just our orbital curiosity. It is a living document of the violent forces that sculpted our solar system's final frontier, and a reminder that even in the deepest cold, the potential for dramatic change is always waiting. That dramatic orbital swing may hold the key to its strangely mottled face. The sixth mystery of Orcus is written in color, a curious dichotomy painted across its frozen surface. This is not a world of uniform shade. Instead, it displays a noticeable gradient, a subtle but definite shift from a reddish hue in some areas to a more neutral, almost grayish color in others. On many other distant bodies, space weathering creates a single, consistent rusty cloak. But on Orcus, this processing is patchy, creating a world of 2 distinct complexions. The primary artist behind this color scheme is solar radiation. When the sun's high-energy particles bombard ices like methane and nitrogen, they break the molecules apart. This triggers a complex chemical chain reaction, slowly baking the pristine ice into a reddish carbon-rich gunk known as tholins. It is the same process that turns a white piece of bread into dark toast over time. So why has this cosmic toasting occurred so unevenly across Orcus? One possibility is its extreme topography. Deep craters and high mountain ranges could create permanent shadows and sunlit slopes, creating vastly different temperature zones. The areas that receive more of the sun's feeble but persistent radiation would cook faster, turning a deeper red, while the permanently shadowed valleys might retain their original neutral-colored ice. Another compelling idea points to its chaotic orbit. Perhaps recent, small impacts have scarred the surface, blasting away the old, reddened crust to reveal fresh, bright ice from underneath. This would create a splatter pattern of gray on a reddish canvas, a temporary record of recent cosmic collisions. But the most exciting possibility is that we are seeing the faint signs of that sluggish geological activity. Could slow-moving glaciers of water ice be oozing across the landscape, covering the reddened terrain with cleaner, neutral-toned material? Or are the faint whispers of cryovolcanic seepage resurfacing small patches of the ground, effectively spot-cleaning the world's face? This color dichotomy is more than just a visual curiosity. It is a direct map of the active processes, both internal and external, that are still shaping this remote dwarf planet. The patchy reds and grays are a silent testimony to a world that is not quite dead, but slowly, silently changing under the distant sun. Buried beneath its icy shell lies a secret that defies the very nature of the outer solar system. The seventh mystery of Orcus is its unexpectedly high density. For a world so distant and cold, we anticipate a fluffy composition, a mix of rock and ice that would give it a relatively low density, like a cosmic snowball. But initial calculations tell a different story. Orcus appears to be surprisingly dense, and in the language of planetary science, density is a direct clue to composition. A higher density means there is less ice and more rock packed into its interior. This implies that Orcus possesses a disproportionately large, heavy core of silicate rock, a finding that sends ripples through our understanding of how such objects form. How does a world in the frozen Kuiper Belt, a region dominated by primordial ices, end up being so rock-rich? One dramatic explanation points to a violent origin story. Imagine a colossal impact in the ancient past, a collision so powerful that it blasted away the majority of the original body's outer, icy mantle. What remained was the dense, rocky core, which then slowly re-accreted a thin new shell of ice over billions of years. In this scenario, Orcus would be the surviving heart of a much larger, obliterated protoplanet. Another possibility challenges our view of its internal structure. Perhaps Orcus is partially differentiated. This means the rock and ice inside it never fully separated into distinct layers, like a poorly mixed cake where pockets of flour remain clumped together. Instead of a neat, concentrated core, its rocky material might be scattered throughout its volume, intertwined with the ice in a way that creates an overall higher density without a single, massive core. This would suggest a much more complex and geologically interesting interior than we ever presumed for a small, distant world. Could its rocks be composed of unusually dense minerals, different from the material we typically find in the asteroid belt? The high density of Orcus forces a fundamental question. Is it a unique relic of a forgotten cosmic catastrophe? Or is it evidence that the building blocks of the outer solar system were far more varied and rock-rich than our current models allow? The weight of this small world carries the heavy burden of rewriting its own history. Yet these surface colors are more than just a visual map, they are a direct source of thermal intrigue. The eighth mystery of Orcus lies in its temperature, or more precisely, in its baffling temperature anomalies. Our basic models predict that a world so far from the sun should have a uniform, unbelievably cold surface, a deep freeze hovering just a few dozen degrees above absolute zero. But the data we have suggests a more complicated story. The surface temperature of Orcus does not always match what we would expect based solely on its distance from the sun. There are unexplained variations, pockets of warmth and cold that defy simple explanation. This thermal fingerprint points to a world with a dynamic and active surface, not a passive and uniformly frozen one. So what could be causing these strange hot and cold spots? The most immediate suspect is the stark contrast between its bright and dark terrains. Think of a black car parked next to a white car on a sunny day. The black car absorbs more sunlight and becomes significantly hotter. On Orcus, the dark, charcoal-gray regions, perhaps rich in carbonaceous material, are likely soaking up the meager solar energy and becoming slightly warmer than their brilliant, highly reflective neighbors. These bright, icy patches act like cosmic mirrors, bouncing most of the sunlight back into space and remaining in a deeper chill. But the plot thickens with the concept of thermal inertia, which is simply how slowly or quickly a surface heats up and cools down. A material with high thermal inertia, like solid rock, takes a long time to warm up but also a long time to release its heat. A material with low thermal inertia, like a fluffy, porous layer of ice dust, heats up rapidly in the sun but also loses that heat the instant it is shaded. The surface of Orcus could be a patchwork of these different materials. An area covered in a fine, insulating powder might exhibit wild temperature swings, while a solid sheet of water ice would maintain a much more stable and predictable cold. This could create unexpected thermal hotspots in sunlit regions that are completely different from shaded areas of identical composition. The most thrilling possibility, however, points inward. Could we be detecting the faint, residual warmth from the dwarf planet's own interior? If Orcus does possess a large, rocky core as its density suggests, that core could still be generating heat from the decay of radioactive elements like uranium and thorium. This radiogenic heat, a faint whisper from a warm heart, could be slowly seeping up through the icy mantle. It would not be enough to create oceans, but it might be sufficient to subtly warm the base of the ice shell, causing localized melting or at least creating a thermal gradient that manifests as a slight temperature anomaly on the surface. These thermal mysteries are a powerful reminder that a world is not defined by sunlight alone. The internal fires of its creation and the intricate texture of its surface are writing their own hidden story in heat. A story we are only just beginning to read from across the vast, cold gulf of space. The warmth of a world can reveal its secrets, but the bond between Orcus and its moon Vanth asks a deeper question about their very origin. The ninth and perhaps most foundational mystery is how this unlikely pair came to be. How does a bright, icy dwarf planet end up with a dark, dusty companion nearly half its size, locked in such a close and stable embrace? Scientists are piecing together a cosmic origin story, and three competing theories dominate the investigation. The first and perhaps most intuitive idea is that of a giant impact. This is the same process believed to have formed our own moon, when a Mars-sized body slammed into the early Earth, blasting a cloud of debris into orbit that later coalesced. For Orcus, a similar catastrophic collision in the ancient Kuiper Belt could have torn material from its outer layers, which then clumped together to form Vanth. This theory neatly explains their synchronous orbit and the moon's close proximity, but it hits a major snag. If Vanth was born from Orcus, why are their surfaces so dramatically different? A child made from its parents' material should share a family resemblance, not possess the alien, charcoal-black complexion of a complete stranger. The second theory, gravitational capture, offers a solution to that compositional riddle. In this scenario, Vanth was an independent traveler, a lone wanderer from the vast population of dark Kuiper Belt objects. A delicate gravitational dance, a cosmic slowing of orbits, could have allowed Orcus to gently snare this passing object, pulling it into a permanent partnership. This perfectly accounts for their starkly different colors and surface materials, as if two strangers from different neighborhoods decided to share a home. Yet capture has its own difficulties. For such an event to result in the nearly circular, tidy orbit we see today is incredibly fortuitous, a gravitational balancing act that is hard to achieve without the two objects either crashing together or flinging each other apart. The third possibility is co-formation, where both Orcus and Vanth condensed from the same swirling cloud of gas and dust at the dawn of the solar system, emerging as a binary pair from the very beginning. This would be a more peaceful origin, but it struggles even more profoundly with their mismatched appearance. Two siblings born from the same primordial nursery should be made of the same stuff. So we are left with a puzzle where each piece of evidence seems to contradict another. Their different compositions scream capture, but their similar size and stable orbit whisper impact. Solving this mystery is not just about one distant world and its moon. The answer will tell us whether the early Kuiper Belt was a place of violent, planet-shattering collisions, a quiet dance of independent objects, or a complex mix of both. The silent bond between Orcus and Vanth holds the key to understanding how all the binary worlds at the edge of our solar system were born. This cosmic partnership raises a profound question about company. Is the dwarf planet Orcus truly alone with its single, large moon Vanth, or are we simply unable to see a hidden family of smaller satellites? The 10th mystery is a search for ghosts, the possibility of undiscovered moons circling this distant world. When we look at other large residents of the Kuiper Belt, we find they often host complex mini-systems. Pluto, for instance, has 5 known moons, Haumea has 2. This makes the apparent binary simplicity of Orcus and Vanth somewhat unusual for an object of its size. Their tight, two-body dance feels almost too neat, leading scientists to wonder if fainter, smaller partners are waiting to be found. The challenge in spotting them is immense. Trying to see a tiny, dark moon near Orcus from Earth is like trying to spot a single grain of black sand next to a pebble from thousands of miles away, with both objects illuminated by nothing more than a distant candle. The faint light we receive is already at the limit of our most powerful telescopes. A small moon would be lost in the glare of its parent world, a faint whisper drowned out by a shout. So what would the discovery of such moons reveal? If a collection of small satellites exists, it would be powerful evidence for that giant impact theory. They would be the leftover debris from the cataclysmic collision that supposedly created Vanth, fragments that never coalesced into a larger moon and instead settled into stable orbits around the pair. Their positions and paths would be a frozen record of that ancient violence. Conversely, if meticulous searches continue to find nothing, that absence would be equally telling. It would strengthen the case for Vanth being a captured object, an event that would have been far less likely to leave behind a cloud of attendant debris. Even a single, small additional moon would be a scientific goldmine, not just for its origin story. The precise gravitational tugs of a smaller moon on both Orcus and Vanth would allow astronomers to perform a cosmic weigh-in. By carefully tracking their orbital dances, we could calculate the mass of the entire system with incredible accuracy. And mass, combined with our estimates of size, gives us the true density. This is the key that unlocks the door to internal structure. A precise density measurement would tell us definitively whether Orcus is a fully differentiated world with a heavy rocky core or that partially mixed geologically complex body. The hunt for these unseen moons is more than a celestial census. It is a direct investigation into the formation and inner nature of this distant world. The silence we hear from the darkness around Orcus and Vanth is itself a message, one we are only now learning how to decode. That search for hidden moons relies on reading faint signals of light, but the light reflected by Orcus itself holds an even deeper code. The 11th mystery is locked within its spectral signature, a unique fingerprint of its surface composition written in wavelengths we cannot see. Our telescopes have broken down this faint glow, confirming the presence of familiar water ice and hints of methane. Yet the data contains stubborn, unidentifiable lines and dips, features that do not correspond to any known ices or minerals in our earthly databases. It is like having a detailed genetic code for an unknown animal, where most of the sequences are recognizable but key segments are completely alien. This spectral puzzle suggests the surface of Orcus is coated with materials we have never encountered before. One compelling explanation points to exotic ices. In the profound cold and near vacuum of the Kuiper Belt, common molecules can arrange themselves into crystalline structures that are completely unstable on Earth. Imagine a form of water ice that exists not as the familiar hexagonal snowflake, but as a different, more compact atomic lattice, one that only forms at temperatures hundreds of degrees below zero. Methane or nitrogen could also be frozen into exotic states, creating spectral signatures that our laboratories have never had a chance to study. Alternatively, the unknown features could be the calling card of complex organic molecules. The constant bombardment of cosmic rays on simple surface ices like methane is a known recipe for creating tholins, the reddish organic gunk. But what if the process on Orcus, operating in its unique environment over billions of years, has produced a particularly complex or unusual blend of these carbon-rich compounds? The spectral data might be hinting at a probiotic chemistry more intricate than we ever thought possible in such a frozen, airless place. Solving this puzzle is not just about labeling what is on one distant world. Cracking this spectral code could force us to create entirely new categories of materials in our textbooks. It would reveal that the outer solar system is a chemical laboratory with its own unique rules, capable of forming substances that do not and cannot exist anywhere else. The unknown lines in Orcus's light are a direct challenge to our knowledge, a quiet signal from the edge of darkness telling us that we have only just begun to catalogue the true diversity of our cosmic backyard. These unidentifiable chemical signatures hint at a world capable of profound change, and perhaps the most dramatic evidence of that is written across its very landscape. The 12th mystery of Orcus is the potential for cryovolcanism, a concept that turns our understanding of volcanoes completely upside down. Forget fiery mountains spewing molten rock. On this frozen world, volcanoes would erupt with a chilled slurry of water, ammonia, and methane, a thick, antifreeze-laden lava that would instantly freeze into brilliant, gleaming plains. The most compelling clues are those bright, reflective patches that stand out so starkly against the reddish terrain. They look exactly like fresh geological deposits, as if someone painted the surface with a clean, white brush. Could these be the frozen flows from ancient cryovolcanoes, the remnants of eruptions that happened millions of years ago? Or is there a chance, however faint, that Orcus is still geologically active today? Some observations suggest not just bright spots, but potential flow-like features, gentle ridges and lobes that resemble the slow creep of a glacier. If this is cryovolcanism, it demands an incredible internal heat source. So far from the sun, the warmth must come from within. One possibility is the persistent decay of radioactive elements like uranium and thorium locked deep in its rocky core. This radiogenic heat is a slow, steady candle that can burn for billions of years, potentially providing just enough energy to maintain a slushy, subsurface ocean trapped between the rocky core and the icy crust. Another, more dynamic source could be tidal heating. The gravitational pull between Orcus and its substantial moon Vanth constantly flexes both worlds, stretching and squeezing their interiors. This friction generates heat, the same process that powers the spectacular cryovolcanoes on Jupiter's moon Io, though on a much quieter, more sluggish scale for the distant Orcus system. The discovery of active cryovolcanism here would be a revolution. It would mean that even in the solar system's most remote and frozen reaches, worlds can harbor the three key ingredients for life as we know it. Liquid water, a source of energy and complex organic chemistry. The cryovolcanic plumes would be a direct pipeline, transporting material from a hidden, potentially habitable ocean right up to the surface. This would transform Orcus from a frozen fossil into a prime target in the search for life beyond Earth, a silent, dark world that might just be hiding a secret sea. The way Orcus spins tells a story of its own, and the plot is full of strange twists. The 13th mystery is encoded in its rotational light curve, the rhythmic pulse of its brightness as it turns in the void. By tracking these subtle changes in reflected light, astronomers can map the world's shape and surface features from across the solar system. The pattern they have found is anything but simple. The light curve shows significant, complex variations, far more than you would expect from a smooth, round sphere. This is the signature of a world with a deeply uneven complexion or a profoundly distorted form. A simple, elongated shape like a stretched-out watermelon would create a predictable two-peaked light curve, but the data from Orcus is more jagged and unpredictable, hinting at something much more intricate. One possibility is that we are not looking at a single, coherent shape at all, but at the shattered remains of one. A colossal impact in the ancient past could have left Orcus with a highly irregular, lumpy form, a cosmic potato spinning end over end. Its gravitational field would be just strong enough to hold this misshapen mass together, but not strong enough to squash it into a neat sphere. Every rotation would present a different, uneven profile to our telescopes, creating a chaotic pattern of bright and dim. Alternatively, the explanation may lie entirely on its surface. Imagine a world painted with a wild patchwork of terrains. Vast, brilliant plains of freshwater ice could be situated right next to enormous, dark basins of ancient carbon-rich gunk. As each region rotates into view, the total brightness would swing dramatically from a faint glimmer to a brilliant flash. This would be like watching a tumbling ball with one half made of polished mirror and the other half of black velvet. The most subtle and intriguing possibility involves its companion, Vanth. The gravitational tug of war between the dwarf planet and its sizable moon does not just govern their orbit. It could also induce a slight wobble in the spin of Orcus, a gentle nodding motion known as libration. This wobble would subtly change the angle at which we see its surface features from Earth, adding an extra layer of complexity to the light curve and making a fundamentally regular shape appear bizarrely irregular from our distant vantage point. Untangling this signal is like trying to discern the true shape of a tumbling object in a pitch-black room by watching only the flicker of a single candle reflected on its surface. Is the flicker caused by the object's form, by patches of different reflectivity, or by an unsteady hand holding the candle? The complex pulse of light from Orcus holds the answer, a rhythmic code waiting to be broken, revealing whether this distant world is a cosmic fragment, a painted marvel, or a partner in a delicate, wobbling dance. This complex spin and mottled face lead us to a deeper chronological puzzle. The surface of Orcus presents us with a profound contradiction in time. One part of its landscape appears ancient, a fossilized relic from the solar system's dawn, while another looks as if it was formed only yesterday. How can a single world wear two different ages at once? The evidence for an ancient surface is overwhelming. Billions of years of relentless bombardment should have left it pockmarked with craters, a cosmic battlefield scarred by countless impacts. Furthermore, the constant rain of cosmic radiation should have baked its volatile ices into that familiar, dark red tholin layer, a process that takes eons. The presence of these dark, reddish regions confirms that much of Orcus is indeed incredibly old, a pristine time capsule from the early Kuiper Belt. Yet, this story is directly challenged by those brilliant, reflective patches of water ice that gleam with impossible purity. They look clean, fresh, and startlingly new, completely untouched by the space weathering that has darkened their surroundings. This is the surface age paradox. Is Orcus a dead world, or does it possess a hidden engine of renewal? One of the most compelling solutions is cryovolcanism, which we explored earlier. A slushy, antifreeze-rich ocean deep beneath the ice could occasionally breach the crust, flooding vast areas with fresh, bright material that instantly refreezes, effectively erasing the old, cratered terrain and painting over it with a new, young surface. This would mean the world is geologically alive, capable of erasing its own history. Another possibility involves a much slower, more subtle process linked to its wild orbit. As Orcus swings closer to the Sun during its long year, the faint increase in solar energy might be enough to trigger a global-scale seasonal cycle. Ices like methane could sublimate from warmer, darker regions, traveling in a tenuous vapor across the landscape before recondensing as a bright, clean frost in the permanently shadowed cold traps. This would be a continuous, self-cleaning process, a slow-motion weather cycle that constantly refreshes specific areas without any internal heat required. There is also the chance that we are seeing the result of tectonic activity. The slow freezing of a subsurface ocean or the gentle heating from a radioactive core could cause the icy crust to crack and shift. These movements would expose fresh ice from below, creating bright fault lines and scarps across the ancient, darkened crust, like the white flesh of a cracked rock. The surface age paradox forces us to abandon simple labels. Orcus is neither entirely dead nor vibrantly alive in the way we understand. It exists in a third state, a sluggish, geological twilight where change operates on timescales of millions of years. Its face is a palimpsest, a parchment where the original, ancient text is still visible, but where a newer, brighter story has been partially written over the top. That ancient, scarred surface might hold the faintest echo of a structure we never expected to find so far from the giant planets. The 15th mystery of Orcus is the ghost of a potential ring system, a delicate, unseen halo of dust and ice that could orbit this tiny world. We once believed rings were the exclusive domain of gas giants like Saturn, but the discovery of rings around smaller, distant bodies like the centaur Chariklo and the dwarf planet Haumea shattered that assumption entirely. These findings prove that rings can form and persist around surprisingly small objects in the frigid outer solar system, opening a realm of thrilling possibility for Orcus. So what could possibly create and sustain such a delicate feature around this distant dwarf planet? One of the most dramatic origins would be a recent, violent impact. A collision with a smaller object could have blasted a cloud of fine debris into space. If this debris were released within a specific distance from Orcus, a region known as the Roche limit, the dwarf planet's gravity would prevent the particles from clumping back together into a moon. Instead, they would be condemned to spread out into a thin, temporary ring, a shimmering memorial to a recent cosmic crash. Another, more stable mechanism involves the gentle shepherding of tiny, unseen moons. Imagine a small satellite orbiting just beyond a potential ring. Its gravity would act like a cosmic sheepdog, nudging stray particles and confining them to a narrow, well-defined band. This is how many of the intricate rings around Saturn maintain their sharp edges, and the same physics could easily be at work in the Orcus system, with a moon too small for us to detect performing this delicate gravitational ballet. Perhaps the most intriguing possibility involves the dwarf planet itself. If cryovolcanic activity is real, then Orcus could be actively venting fine particles of water ice and other frozen gases from its surface. These jets of material, if they reached escape velocity, could inject a steady stream of fresh particles into orbit, creating a faint, constantly replenished ring of its own making. While our most sensitive observations have yet to find any evidence of rings around Orcus, the silence is not a definitive no. Our current telescopes operate at their absolute limits when studying such a distant, faint object. A thin, dark ring composed of fine dust would be virtually invisible from Earth. The question remains tantalizingly open, a spectral suggestion waiting for a future spacecraft's camera to either confirm its existence or finally lay the ghost to rest. The solar wind carves its own invisible story into the surface of Orcus. This is the 16th mystery, a silent and constant barrage of charged particles streaming from the sun that meets no global magnetic field to deflect it. Without a protective magnetosphere, these high-energy protons and electrons slam directly into the frozen ground. The question is not if this interaction occurs, but what strange and subtle alchemy it performs on this airless world. One immediate effect is a process known as sputtering. Imagine each solar wind particle as a microscopic cannonball. When it strikes a molecule of water ice on the surface, it can knock that molecule clean off into space. Over billions of years, this relentless sandblasting could be slowly eroding the surface, atom by atom. This process might even be responsible for creating an incredibly thin, temporary shroud around Orcus, an exosphere of ionized gas. This would not be a true atmosphere you could breathe or even feel, but rather a fleeting cloud of individual atoms leaping from the surface only to be swept away by the solar wind or fall back down as a microscopic frost. This sputtering could also be a key artist in the surface's darkening. The constant bombardment breaks apart the delicate bonds in water and methane ice, freeing up oxygen and carbon atoms. These atoms can then recombine into complex dark carbon compounds, efficiently accelerating the creation of those reddish tholins we see. It is a form of cosmic tanning where the solar wind, not ultraviolet light, is the primary agent that slowly bronzes the ice. Yet this weathering process might be highly selective. The bright, reflective patches could be areas where the ice is so pure and hard that sputtering is less effective, or where recent geological activity has simply outpaced the slow stain of radiation. Understanding this intricate dance between the solar wind and the ice is like learning a new language of erosion. It is the key to correctly reading the surface of not just Orcus, but every other denizen of the Kuiper Belt. Is a dark red color a sign of great age, or simply an indication of a surface composition that is uniquely vulnerable to this invisible weathering? The answer determines whether we are looking at a genuine fossil or a world still being actively sculpted by the faint breath of the sun. That solar wind weathering may be the cosmic artist, but the final portrait of Orcus is painted in stark contrasts of light and shadow. The 17th mystery is written in its inconsistent reflectivity, a global albedo map that refuses to tell a simple story. While those brilliant patches shine with the intensity of freshly fallen snow, the dwarf planet's overall reflectivity is only moderately high, a puzzling average that hides a world of extremes. This is not a uniformly bright ball of ice, nor is it a consistently dark world. It is a complex mosaic where some areas act like celestial mirrors and others like cosmic charcoal. So what creates this patchwork quilt of light absorption and reflection across a single, frozen sphere? One compelling theory suggests a thin, global veneer of dark dust. Picture a fine layer of soot or carbon-rich powder settled over the entire world, a blanket that dims the natural brightness of the underlying ice. In this scenario, the famous bright spots are not areas of special composition, but simply places where this dark blanket has been stripped away. A recent impact could have blasted the dust off a crater floor, revealing the pristine ice beneath. Or a cryovolcanic flow could have welled up and resurfaced a vast plain, effectively power washing a section of the landscape and leaving it gleaming. The competing theory argues that the surface material itself is fundamentally variable from place to place. Perhaps the dark regions are not a superficial coating, but vast expanses of primordial, radiation-baked tholins, a thick crust of ancient organic gunk. The bright areas, then, would be genuine outcrops of purer water ice exposed by geology or impacts. This would mean we are seeing the true, diverse bedrock of Orcus, not just a dusty covering. Creating a detailed albedo map is the key to unlocking this mystery. It would be like creating a weather map of reflectivity, showing exactly where the world is bright and where it is dark. By overlaying this map with topographical data, we could see if the bright spots consistently lie in low-lying craters on high mountain peaks or along sweeping plains. If the bright areas align with specific geological features, it would be powerful evidence for active processes continually refreshing the surface. If the dark and bright regions appear random, it might point toward that blanket of dust distributed by micrometeorite impacts and the faint solar wind. This puzzle of light and dark is far more than a visual curiosity. It is a direct window into the geological vitality and history of this remote world. Is Orcus a static body slowly being soiled by cosmic dust, or is it a dynamic world actively fighting to keep its face clean, its bright scars telling a story of a tumultuous and ongoing transformation? But that faint hope of hidden water leads us to the 18th and perhaps most profound mystery of all. Could this frozen, airless world secretly cradle a liquid ocean beneath its crust? The possibility seems to defy all logic, yet the science is compelling. For an ocean to exist on Orcus, two things are required: a source of heat to keep the water from freezing solid, and an antifreeze agent to lower its freezing point dramatically. The first ingredient, heat, could come from the slow and steady decay of radioactive elements like uranium and thorium locked deep within its rocky core. This radiogenic warmth is a faint, persistent fire, a dying ember from the world's formation that could still be smoldering after billions of years, providing just enough energy to maintain a slushy layer between the rock and the ice. The second ingredient is the antifreeze itself. Simple water ice could never remain liquid at these distances, but if that water is mixed with chemicals like ammonia or salts, its freezing point can plummet by hundreds of degrees. A briny, ammonia-rich soup could easily stay liquid in the profound cold, trapped under a shell of ice that might be dozens of miles thick. This is the tantalizing equation: internal heat plus chemical antifreeze equals the potential for a stable subsurface sea. The mystery, of course, is that we have absolutely no direct evidence. Our telescopes cannot peer through that icy shield. We do not know the exact thickness of the ice shell, the precise amount of internal heat, or the detailed composition of the interior. These are the vital numbers that would turn this thrilling speculation into confirmed fact. Yet the implications are staggering. If a liquid ocean exists on Orcus, it would instantly catapult this distant dwarf planet into an elite category of worlds, prime candidates in the search for life beyond Earth. Such an ocean would be a dark, isolated abyss, cut off from the surface and the sun for eons. But around hydrothermal vents on its rocky floor, where mineral-rich water seeps from the core, the basic ingredients for life, water, energy, and chemistry could converge. It is a haunting thought that in the absolute darkness under the ice of a world at the edge of nowhere, something might be stirring. That hidden ocean would be a relic of profound internal change, but the true origin of Orcus might be written in the paths of its unseen kin. The 19th mystery asks whether this dwarf planet is a solitary survivor or the patriarch of a shattered dynasty. Scientists call this a collisional family, a group of Kuiper Belt objects that share nearly identical orbits and compositions, all born from the same cataclysmic impact that shattered their parent body billions of years ago. Finding such a family for Orcus would be like discovering the scattered pieces of a cosmic fingerprint, offering undeniable proof of a violent birth. The evidence would be clear: a collection of smaller, fainter worlds trailing along a similar path around the sun, their spectral signatures matching the unique mix of bright ice and dark material we see on Orcus itself. This would perfectly explain its high density and its strange binary system, painting a picture of a colossal collision that blasted away icy mantle material to form Vanth and the other family members, leaving behind the dense, rocky core we now call Orcus. Yet, despite careful searches, no such family has been conclusively found. The space around its orbital path appears strangely empty of recognizable relatives. This absence is a deep and puzzling silence, So where did everyone go? One possibility is that the family exists, but its members are simply too small and faint for our current telescopes to detect. They could be countless mountain-sized chunks of debris, lost in the vast darkness and invisible to all but the most powerful future observatories. Another, more dynamic explanation is that the family was scattered. In the chaotic gravitational environment of the early Kuiper Belt, the gentle tugs from giants like Neptune could have slowly perturbed the orbits of these fragments over eons, dispersing them across a much wider volume of space. Their orbital resemblance has been erased, making them impossible to link back to Orcus through orbit alone. The most radical possibility, however, is that the entire premise is wrong. Perhaps Orcus was not formed by a giant impact at all. Maybe it accreted peacefully, a solitary world that grew slowly from the primordial disk without a world-shattering catastrophe. Its high density could then be a primordial feature, meaning the building blocks in this part of the solar system were simply richer in rock than we ever anticipated. Solving this family mystery is more than an academic exercise. It is a direct investigation into a single, violent day in the deep past of our solar system. Did Orcus lose its family to time and gravity, or was it always an only child, a solitary world whose very existence challenges our stories of how planetary bodies are born and destroyed in the frozen dark? Methane should not be able to stay here. That is the 20th and deeply puzzling mystery of Orcus. This simple hydrocarbon ice is incredibly volatile, eager to leap from a solid directly into a gas even in the faint warmth of the distant sun. On a small world with such a weak gravitational pull, that gaseous methane should have escaped into space eons ago, vanishing without a trace. Yet the spectral data insists that methane is still there, clinging to the surface of this ancient world. Its stubborn presence is a profound clue, pointing to a hidden stability we do not yet understand. So how does Orcus manage to hold onto it? One possibility is that the methane is not lying loose on the surface like a frosting, but is locked away in a chemical prison. Scientists call these structures clathrate hydrates, or more simply, cage compounds. Imagine the crystalline structure of water ice forming a microscopic jail cell with a single molecule of methane trapped inside each one. This methane hydrate is far more stable than pure methane ice, requiring much more energy to break apart and release its captive. On Orcus, much of the surface methane could be bound in this form, effectively fossilized within the water ice bedrock and protected from the gentle but persistent tug of solar heating. A far more dynamic explanation is that the methane is not old at all, but is being constantly renewed. This is where the theory of cryovolcanism returns with compelling force. If a slushy, ammonia-rich ocean does slosh beneath the crust, it could be laden with dissolved methane. Occasional eruptions or slow seepages would carry this fresh methane to the surface, where it instantly freezes, replenishing the supply as quickly as it is lost to space. In this scenario, the surface methane is not a relic, but the fleeting byproduct of an active, breathing world, its presence a direct signal from a hidden interior. The simplest answer, however, might be the most surprising. Perhaps the surface of Orcus is just cold enough, and has always been cold enough, to allow even pure methane ice to persist. The retention of volatile ices is a delicate balance between a world's temperature, its gravity, and the specific properties of the ice itself. While Orcus is not massive, its great distance from the Sun might place it just below a critical threshold where methane can survive for billions of years in certain permanently shadowed craters, places where the temperature never ever rises. The methane we see could be the last remnants of the dwarf planet's original inventory, a primordial stain that has somehow, against all odds, endured. Each of these possibilities tells a completely different story about Orcus. Is it a world with a stable, cage-like crust preserving its ancient chemicals? Is it a geologically active body constantly venting its internal gases? Or is it simply the coldest and most efficient deep freezer in the entire solar system, a place where even the most flighty of ices have nowhere left to run? The answer transforms this frozen speck from a passive bystander into an active participant in its own destiny, a world that has mastered the art of holding on. The very structure of Orcus is a secret locked deep within its frozen heart. We stand on the outside, looking at a distant, speckled globe, forced to deduce the entire internal architecture of a world from a handful of faint clues. Is it a simple, homogeneous ball of rock and ice mixed together like a cosmic fruitcake, or has gravity done its work, pulling the heavy elements inward to form a dense, rocky core, while the lighter ices rose to create a distinct, separate mantle? This is not just an academic question. The answer dictates whether Orcus is a geologically dead fossil or a world with hidden potential. A differentiated structure with a concentrated core is a prerequisite for that subsurface ocean we dared to imagine. It means the planet was once warm enough to melt from the inside out, allowing its materials to separate into layers, a process that releases immense gravitational energy and leaves behind a complex, structured world. Our primary tool for this internal investigation is its bulk density. We know its mass from the orbital dance with Vanth, and we have estimates of its size from telescopic observations. Dividing one by the other gives us that crucial number, a density that seems surprisingly high. This points toward more rock and less ice than we would expect, strongly hinting at differentiation. But density is an average, a single number for the entire world. It cannot tell us how that rock is arranged. Is it a single, solid sphere of silicate at the center, or are there chunks and layers of different materials scattered throughout? Perhaps the interior is a strange, partially differentiated mess, with vast pockets of rock still suspended in the ice, creating a planetary structure unlike any we have closely studied. The gravitational tug of war with its moon Vanth offers another subtle clue. By meticulously tracking Vanth's orbit, astronomers can map the tiny gravitational irregularities of Orcus itself. A perfectly uniform interior would create a smooth gravitational field. But if the interior is lumpy, with concentrations of mass hidden deep below the ice, it would cause Vanth's path to wobble in a specific, detectable way. These minute tugs are the fingerprints of the internal structure, a ghostly signal of the world's hidden anatomy. The true revelation will only come from a visitor. A future spacecraft orbiting Orcus could perform a gravity science experiment, precisely tracking how the probe's own orbit is perturbed by the dwarf planet's gravitational field. This would allow scientists to create a detailed density map of the interior, effectively giving Orcus an MRI scan from millions of miles away. We would finally see the hidden boundaries between rock and ice and know for certain if this distant, frozen world has a warm, layered heart. The stark differences between Orcus and Pluto are a cosmic puzzle in their own right. How can two worlds so similar in size, orbit, and likely origin end up on such divergent evolutionary paths? This is the 22nd Great Mystery, a comparative enigma that uses Orcus as a natural control experiment to understand the hidden rules governing all dwarf planets. They are celestial twins separated at birth, raised in the same distant neighborhood, yet one breathes a hazy atmosphere while the other appears utterly airless. This single discrepancy forces us to question everything we think we know about these frozen worlds. The most glaring difference is, of course, their skies. Pluto, despite its vast distance, possesses a complex, layered atmosphere of nitrogen and methane that swells and collapses with its seasons. Orcus, by all current measurements, has none. This cannot be explained by size alone, as they are nearly identical in that regard. The answer may lie in the subtle details of their composition. Perhaps Pluto retained more of the volatile ices like nitrogen because it formed in a slightly richer region of the primordial disk, giving it a deeper reservoir of gases to draw upon. Or maybe Pluto's internal heat is simply greater, its radioactive core more potent, providing just enough warmth to keep these ices from permanently freezing to the surface. Their surfaces tell a similarly split story. Both show evidence of bright, reflective plains, but Pluto's landscape is a breathtaking tapestry of nitrogen glaciers, floating water ice mountains, and vast cell-like plains, all hinting at a geologically vibrant world. Orcus, with its more muted color contrasts and potential bright patches, suggests a far quieter existence. Is this because Pluto has a more active interior, or did a cataclysmic impact in its past stir its insides, creating the energy for ongoing change that Orcus never experienced? Even their moons point to different histories. Pluto's system is a complex family of 5 satellites, with the giant Charon implying a violent, singular birth. Orcus has only the single dark Vanth, a moon whose origin remains hotly debated between capture and impact. This suggests that the early Kuiper Belt was a place of varied social dynamics, where some worlds built families through collision, while others adopted solitary travelers. By holding these two twins side by side, scientists are not just studying two individual objects, they are deciphering the fundamental levers of planetary evolution. Is the presence of an atmosphere dictated by a critical threshold of mass, a specific blend of internal heat, or simply the luck of a gentler collisional history? Does geological activity require a large moon for tidal heating, or can a world's own radioactive heart provide enough fire? Orcus, the quieter twin, provides the baseline, the silent control in the experiment. Its stark contrasts with the dynamic Pluto reveal that the line between a living world and a dead one is not drawn by size or distance alone, but by a delicate and invisible balance of chemistry, heat, and history that we are only beginning to perceive. But the faint breath of the solar wind is only part of a much larger storm. Bombarding Orcus from far beyond our own sun is a ceaseless rain of galactic cosmic rays, particles accelerated to nearly the speed of light by distant supernova and black holes. These are not mere protons from the sun, but the nuclei of heavy elements like iron, screaming across the galaxy with energies that dwarf anything our local star can produce. When these microscopic bullets strike the frozen ices of Orcus, they do not just sputter atoms away. They shatter molecules, breaking apart water and methane in a violent, chaotic spray of broken bonds and free radicals. This is the 23rd mystery, a cosmic alchemy that is slowly, over billions of years, cooking the surface into something new and dark. The end product of this relentless radiation bath is a complex, carbon-rich gunk scientists call tholins. Think of it as a cosmic tar, a sticky, organic sludge that forms when simple ices are baked by high-energy radiation. This is the process that gives many outer solar system objects their characteristic reddish-brown hue. But here lies the enigma. The rate and final nature of this transformation on Orcus are completely unknown. Is its surface a kilometers-thick layer of this primordial goo, a crust so ancient and processed that the original ice is buried forever? Or is the tholin layer surprisingly thin, a mere stain on a world that is constantly fighting back against the darkening? The answer changes how we read every single observation. If the dark regions are a thick crust of cosmic tar, then Orcus is a perfectly preserved fossil, its surface a direct window into the chemical processes of the early solar system. But if the tholin layer is thin and patchy, it means other forces are actively at work. Perhaps cryovolcanic flows are regularly erupting, covering the old, dark crust with bright new ice faster than the cosmic rays can darken it. Maybe its wild orbital swings trigger global resurfacing events, where sublimation and recondensation of ices effectively scrub the surface clean in a slow-motion cycle. The color of Orcus is not just a color, it is a clock. The depth of its red tint is a measure of how long that patch of ground has been exposed to the galaxy's fury. A uniformly dark world would tell one story, a story of geological death and passive acceptance. A world of stark contrast like Orcus tells a far more complicated tale. Its mottled face is a battlefield, a record of the eternal war between the darkening forces of the galaxy and the hidden, renewing forces of the world itself. Solving this cosmic ray-weathering riddle does more than explain one dwarf planet. It gives us the universal key to interpreting the surfaces of every dark, distant body from here to the edge of interstellar space. The silent paths of distant worlds may be tracing the shadow of a giant. The 24th mystery of Orcus is the gravitational sculpting hypothesis, the theory that its current orbit is not a product of chance, but a deliberate signature carved by a hidden hand. This idea proposes that the peculiar alignment of Orcus and several other extreme Kuiper Belt objects points to the existence of a massive, undiscovered planet, a so-called Planet 9, lurking in the profound darkness far beyond Pluto. Orcus, in this grand puzzle, is not just a world but a key piece of evidence, its orbit a fossilized record of a gravitational encounter that reshaped the outer solar system. The clues are written in the geometry of space itself. These distant objects, including Orcus, do not have randomly oriented orbits. Instead, their elongated paths are curiously clustered, as if an invisible shepherd has gathered them and aligned their orbits along a similar direction in space. This kind of ordered arrangement is incredibly difficult to explain through the known gravity of the 8 planets alone. It strongly suggests the persistent, gentle tug of a much more distant and much larger world. Think of it like a hidden magnet beneath a table, subtly aligning iron filings into a specific pattern without ever being seen. Planet 9 would be that magnet, its immense gravity slowly steering the orbits of Orcus and its kin over billions of years, herding them into the strange cluster we observe today. If this is true, then Orcus is more than a dwarf planet. It is a celestial compass needle, pointing directly toward the location of one of the greatest discoveries in modern astronomy. Its orbit is a map, and at the end of that map waits a world larger than Earth, a ghost whose presence we can only infer from the synchronized dance of the tiny, icy objects it commands. Yet the mystery deepens with every observation. Could the same effect be produced by the combined gravity of many smaller, unseen objects, a diffuse cloud of dark mass that collectively mimics the pull of a single planet? Or is this orbital alignment merely a statistical fluke, a temporary gathering that will dissolve over the next few million years? The true nature of Orcus's path forces us to confront a staggering possibility that our own solar system is still largely unexplored, and that a giant world remains hidden in the vast, uncharted territories beyond everything we know. This final question pushes our search for life to its absolute limit. Could the frozen, airless Orcus be in any way habitable? The very idea seems to defy all logic, a contradiction for a world so distant and cold. Yet science forces us to follow the evidence, no matter how strange the path becomes. If a subsurface ocean truly does slosh beneath that icy crust, then the equation changes entirely. The 3 fundamental ingredients for life as we know it could converge in that lightless abyss: liquid water, the universal solvent, chemical energy from hydrothermal vents on the rocky seafloor, and complex organic molecules, the very building blocks of biology, delivered by the cosmic ray, baked tholins on the surface and transported downward through the ice. This is not about finding cities or creatures, but about the potential for microbial life, tiny organisms eking out an existence in total isolation, cut off from the sun for billions of years. The environment they would call home is almost unimaginable to us. It is a place of crushing pressure, eternal darkness, and temperatures that would instantly freeze any earthly creature solid. But life on Earth has proven to be astonishingly resilient, thriving in the superheated water around deep sea vents, surviving in rocks miles underground, and enduring in the bitter dry valleys of Antarctica. These extremophiles show us that life can flourish in conditions we once thought were sterile. The profound mystery of Orcus is not just whether life could survive there, but whether it could ever begin in such a place. Could the slow, patient chemistry of a dark ocean, fueled only by geological heat and the faint trickle of organics from above, ever spark that first, fragile reaction that leads to a living cell? Or is the environment too stable, too quiet, lacking the energetic turmoil that might be necessary to jumpstart biology? Orcus represents a new frontier in astrobiology, a world that redefines the habitable zone. This zone is no longer just the narrow band around a star where liquid water can exist on the surface. It must now include these frozen, distant worlds with secret seas, their warmth generated from within. The existence of life in such a place would mean that the galaxy is not merely dotted with rare oases, but absolutely saturated with potential, that life can ignite in the most hostile and isolated corners of any solar system. So we are left with the ultimate, unresolved enigma. Is Orcus a sterile tomb, a beautiful but dead monument to the solar system's formation? Or is it a silent ark carrying within its frozen heart the faint, slow whisper of a second genesis? Until a spacecraft finally journeys to this distant outpost and listens for that whisper, the 25th and greatest mystery of Orcus will remain, a haunting question mark at the edge of the dark. We have traveled from a single point of light to a world defined by 25 profound enigmas. The journey across these mysteries reveals Orcus not as a static fossil, but as a dynamic scientific frontier. Each puzzle, from its vanished atmosphere and alien moon to its potential hidden ocean, and the ghostly influence of a hypothetical planet 9, intertwines to paint a portrait of incredible complexity. This distant dwarf planet forces us to question the very definitions of a living world and a habitable zone, proving that the most fascinating discoveries are often waiting in the darkest, most unexpected corners of our solar system. The collective weight of these questions makes Orcus an irresistible target for a future spacecraft, a mission that could rewrite textbooks and answer our most profound questions about the origins and potential for life in the cosmos. So we turn the final question over to you. After this journey to the edge of darkness, which of these 25 mysteries captured your imagination the most? Was it the silent bond with its dark moon Vanth, the possibility of a subsurface sea, or the haunting suggestion of a hidden giant planet shaping its path? Let us know your thoughts in the comments below, and subscribe to join us as we continue to explore the greatest unsolved puzzles of our incredible universe.